But there's a little bit more than just grid cells. Okay, because we also have to define where each grid point for the sea level elevation and each grid point for the horizontal velocity is defined. Okay? And this is what we call a staggered numerical grid, because the eta and the u points are not defined at the same level. Okay? And why that is because we have the spatial gradients in both equations. So that's why it makes sense to actually place the u calculation between the calculations predictions for the eta points. So let me just get rid of this. Okay. So, and this is the reason. So this is how we define the horizontal grid. Okay, so we do have our grid cells, which are shown here at the top. And you can point to any of these grid cells with the value for k. K is an integer, full number, and you can say k equals 1 is this grid cell here. K equals it's this one here. K equals 2 is this, and you can go along your channel. Okay, but what we also do is we define that the u grid point for the horizontal velocity is half a grid spacing located to the right, to the east, relative to the sea level grid point. Okay, and this is how it looks like here. And with this definition now we can go through the equation. Okay, for example, we can write the momentum equation using an Eulerian time forward step. Like this, you can say, if you are now in a grid cell called K, for each grid cell, K, the prediction which is on the left-hand side, n plus 1 means it's the prediction for the next time level, okay, is the old value, okay, or the current value if you want to, and then comes the correction, and the correction has the horizontal pressure gradient force. And here, if you are at a u location, you see here at the top, you have to use the gradient is defined by the eta to the right, which is actually k plus 1, okay, minus the eta point to the left, which is actually in the same grid cell as the u. And this is how you define now the spatial gradient. Delta x is the grid spacing, and delta t is the time step. Then you can do the same approach for the second loop using the updated velocity. And this is now a prediction for the sea level elevation. And for the sea level elevation, you have to define which volume you want to bring into the grid cell or export out of the grid cell. And this will be explained on the next slide. Okay, but in principle, you have only two faces. You have one which is on the right and one which is on the left. Okay, and in terms of velocity grid points, one is called k, and the other one is k minus 1. And then just for some additional feature shown here, I just move myself, hang on, I just try to select myself, okay, move myself down here. It's just something that we call the Shapiro filter. I will introduce you to this in the following slides. It's just a little smoothing filter, and we will discuss that as well. It's not absolutely relevant here, but you can also use a filter. So once you've done that, these three steps, Shapiro filter you can leave away or so, but once you've done that, you can actually step forward in time. You've done all your predictions for the next time step, then you move forward in time, and then you can repeat the entire iteration. All right? So this is the principle. This is the core of the numerical finite difference schemes. Okay. So now on the next slide, I just want to talk more about how do you do this bit here on the right hand side of the volume conservation equation.